All right, today's lab is on determination of the molecular weight of an acid. Molecular weight and molar mass are synonymous. Molecular weight was is an archaic form, the one I was raised on. So you may hear me occasionally slip into calling it molecular weight instead of molar mass, but know that they mean the same thing, have the same units of measure. Okay, let's look at some theory first before we dig into the method. The method that we're going to use is called titration. So let's bring it down to where we can see it. Titration. Titration is a technique that spans many different types of chemistries. But they all have one thing in common. Something equals something else. And you might say, this is the known quantity, and you put them together in such a way that you can deduce from the known quantity what is the unknown quantity. Okay? So, in acid-base titration, we are using a known quantity of base to determine the unknown quantity of acid. And this is for our purposes, this is in molar terms. So we know how many moles of base is required to react completely with acid, and knowing the chemistry of the reaction, we can deduce how many moles of acid there are. Okay? We need to do two different titrations in this experiment. Number one, which is here on the board, we need to standardize our base, sodium hydroxide solution. And we're going to use a known acid concentration against an unknown concentration of sodium hydroxide, although we know pretty close to what it is, but we need to know exactly. Now, why do we need to do that? Sodium hydroxide solutions are notoriously unstable over long periods of time. So, you may create a solution of sodium hydroxide at one point in time, and 6 months later come back and it's not that concentration anymore. The reason being that sodium hydroxide reacts with carbon dioxide from the atmosphere. In fact, the carbon dioxide dissolves in the solution and becomes carbonic acid. Okay? And when it does that, then it can react with the sodium hydroxide, and sodium reacts with the carbonate, and the hydrogens react with the hydroxyls and gives you water. This is characteristic of all acid-base reactions. A base plus an acid equals water and a salt. This is the definition of a salt, the result of an acid-base reaction. This is no longer able to act as a base, or the base that you think you have. Right? So, in fact, part of the sodium hydroxide now has been neutralized. And if you think you have a concentration of the base, you no longer have that much. Some of it has been converted to sodium carbonate. Now, that equation is not balanced, but the gist is correct. So we need to determine the exact concentration of sodium hydroxide. And we do it by reacting it with Ch203O2. This is acetic acid. Acetic acid is very stable over long periods of time. So we've established and have purchased a standard concentration of this at 0.873 molar. That's what it was on the day we purchased it, and that's what it is now 3, 4, 5 years later. But we don't know what this one is at this moment. So we're going to perform a reaction to standardize this one, and the consequences, of course, will be sodium acetate over here and water, but we want to focus on this part because this has one hydroxyl and one hydrogen, which means the equal amounts of either react with one another. In fact, to prove it, you just balance the equation. Right? One sodium, one acetate, a hydrogen, and a hydroxyl makes a water. So 1-to-1 ratio. So if we know how many moles of this it takes to neutralize a certain volume of that, then we know that the ratio is 1-to-1, and the number of moles of this required is equal to the number of moles of this that you started with. Another way of putting it is molarity. We're going to have a known volume of this, right? And I'll show you how we get that, right? We have that volume, and molarity times volume equals moles. So M1, let's say M base times volume base equals moles base. And at the point where we have added exactly the same amount of this as that, moles of acid, volume of acid equals moles of acid. And these two numbers are equal. So if this is equal to that, then this is equal to that, and we have an equation here, we can say we don't know what that is, we do know what this is, and we do know what this is because we're going to put 10 milliliters of that in the reaction vessel, and then we're going to titrate to where they are equal, so we'll know the volume, and then we solve for the one unknown. Okay, that gives us the concentration of sodium hydroxide. Now that we have the exact concentration of sodium hydroxide, we can use it to titrate against our acid. We know our acid is citric acid, but we don't know its molar mass. This is the accepted value right here. We're going to determine the molar mass of 3 replicates We're going to repeat the procedure 3 times, and hopefully all 3 of them will agree with each other. And if that's the case, we'll keep all the numbers. If, however, we make a mistake somewhere with one of them, then 2 of them should agree with one another, and then we have to decide what do we do with the one that's not quite what we think, it's not in agreement with the other 2. If it's far enough away from the other 2, then we throw it out as an outlier, but if it's close enough, we average them all together. Okay, so that's how we get the molarity of sodium hydroxide. Now we're going to take that known sodium hydroxide and we're going to take a weight or a mass of citric acid and determine how many moles of citric acid we have. And the magic number is, we know the mass, we titrate to find the moles, do the calculation, and you get your molar mass. And it should be very close to this. Okay, but there's one fly in the ointment here. And the ointment, okay, I'm going to abbreviate. No, I'm not. I'm going to write the formula for citric acid because That's where this is derived from. So what is the formula of citric acid? Well, I could look on the bottle, but it's fun to deduce it. I know citric acid has 3 acid groups. It also has 6 carbons. So there's a carbon here, a carbon here, a carbon there. And each one of these carbons has a carboxyl group on it. A carboxyl group looks like this. Carbon, like that. Each one just like that. And the acidic hydrogen is this one right here. And there's one more over here. Okay. So we've got 3 acidic hydrogens that will be neutralized by titration with sodium hydroxide. I forgot one. This one right here. That hydroxyl group. That hydroxyl is not acidic. Right, so we're only titrating these 3 hydrogens. Now, that's the issue. I'm going to abbreviate this. Well, let's see. The formula would be C6, but it has 3 hydrogens. 3 hydrogens, 6 carbons, and there are more hydrogens, of course, because each one of these carbons has hydrogen on it. 1, 2, 3, 4. One thing about carbon is it has a potential for 4 bonds. So if you see something missing, it's usually hydrogen. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So, how many other hydrogens are there? Well, we've already accounted for 3 of them. Those are the acidic hydrogens. That's why we put them here in front. But let's see, there's 1, 2, 3, 4, 5. Is that it? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. So there are 5 hydrogens that are not acidic. And how many oxygens? There's 1, 2, 3, 4, 5, 6, 7. 7 oxygens. So there's the formula for citric acid. Now you could calculate the molar mass from that, and it would be pretty close to this. I got that off the bottle. Okay? So I'm going to abbreviate this. I'm going to put the 3 hydrogens out here for the acid hydrogens, and then the rest of the molecule is just that. Okay? It's easier to deal with than writing this whole thing out. But if you were to write this out for balancing purposes, you would put this in here. And of course, that's not right anymore. So let's move it over, give us a little more room. Now, why am I going to all this trouble? Because in this case, the ratio of sodium hydroxide moles to moles of citric acid is different. Because you have 3 acid groups now instead of 1 from the acetic acid, you have 3 from the citric acid. So when you react this, you have 3 hydroxyls there. That means these are 3 pluses. That means that group has 3 minuses. So that means sodium is your positive over here with the salt, and the citric acid part has 3 minuses. That means you need 3 positives. So 3 sodiums with that citric acid group, and then how many waters do you have? Well, with 3 sodiums, you need 3 here, which means 3 hydroxyls, 3 hydrogens, 3 waters. Okay, now we have the proper ratio. If we know the moles of sodium hydroxide because we've titrated with a known concentration that we determined in step 1 and a volume that we determined from the titration, then we have moles of base here. But how many moles of acid does that represent? Well, if we say this, right, if you have moles, you can go anywhere you want, right? I've always said that. Then the the ratio now is 3 sodium hydroxide and 1 citric acid. Right? So these cancel, leaves you with 1/3. So the moles of base means that you really only have 1/3 of that as acid, right? So let's just say, this is really ridiculous, but let's say we had 3 moles of base. How many moles of acid would that be? Well, the ratio is 3 to 1, so for 3 of these, you only have 1 of those. So if you had 3 of these, you only have 1 of these. And that's taken into account over here with our chart. So here's moles of base. Moles of acid is going to be 1/3 of the moles of base. Then once you know the moles of acid, you know the mass of the acid, you can do your calculation, mass divided by moles. All right. Okay, so let's see if there are any. I don't think there are any pre-lab questions in here. There are lab questions that you answer afterwards. We'll talk a little bit about that afterwards. And I'll just leave that up there, and we'll get on with the exercise as soon as I check the battery on my camera, because I don't want to run out of battery power and then be talking into a blank camera. So just a second. Okay, we're good. So we can forge ahead, and maybe in 10 or 15 minutes I'll check it again. Okay, so here's our method, and let's get over here and look at the materials that we're going to need. All right. So everything you need for this experiment is right here, and of course you need a balance. We'll talk about that in a second. That's the second part. The first part is, here's your acetic acid, 0.873 molar, and here's your sodium hydroxide, which is nominally 0.75 molar. A year and a half ago, we did this experiment, and it had decreased by a smidge, a little bit. We're going to find out exactly what it is by titrating. All right, here's what we mean by titration. We're going to have a known amount of this acid in our Erlenmeyer flask, a 125 milliliter Erlenmeyer flask. And actually we're going to measure that very accurately with a volumetric pipette, right? It says 10 on it, right? That's because it will deliver, and that's what you may not be able to see it there, TD, to deliver. It will deliver exactly 10 milliliters, and it may say plus or minus 0.04 milliliters. It will deliver that 10 milliliters if used properly. Okay, and I'm going to show you how to do that. So we're going to put the 10 milliliters in here of acetic acid. It's going to go underneath the burette. This is a burette. The burette is designed to deliver and record, and not record, but register a volume of delivery. So it is calibrated from top 0 down to the bottom 50 milliliters. Right, so you read it backwards from a graduated cylinder. So if you go down here and you're between 6 and 7, it's not 7 point something, it's 6 point something is the volume delivered if you start at 0. If you start anywhere else, you just record the volume you started from, record the volume at the end of your titration, and subtract the smaller from the larger, and that's how much volume you delivered. This thing is calibrated for milliliters, and then the finer division is tenths of a milliliter. Okay. So how are we going to tell? Oh, actually, I got one other comment. On this citric acid, I gave you the formula and showed you the three acids, acid hydrogens, but suppose we don't know the formula. How would we know that we have three reactive hydrogens, or acid hydrogens, in that molecule? You do what you call a titration, a stepwise titration. In other words, you measure the pH as you add base to it, right? So the acid is going to be starting off here at a low pH, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Start off down here somewhere, and each time you neutralize one of the hydrogens, you get a change in the shape of the curve. So it's going to start off like this, flatten out, this is the buffer zone, and then it's going to go like that. And then right in the halfway mark here, that's the first hydrogen. Then you're going to go up here, it's going to flatten out again, and it's going to go up again like that. That's your second hydrogen. Right here, right here. That's called the equivalence point. That's when the exact amount of base added in moles is equal to the amount of moles of hydrogens neutralized. But we do that for the first hydrogen, for the second hydrogen, and guess what? It does it again for the third hydrogen. Now we know, without even knowing the formula, we know that we have three acid hydrogens in that molecule. And regardless of what the structure is, we can do this type of calculation without knowing what that Ca represents. Okay? For those of you who are curious, that's how we do it. Now, let's see, I was going to make one other comment. Maybe I better walk back over here and it'll come to me. Yes, I mentioned it before. The equivalence point on that titration curve, you can do that for every reaction, every titration. You could just measure the pH, plot it out, and find exactly where the equivalence point is. The problem with that, it will take forever just to do 3 samples. We want something quicker. So, we know where those equivalence points are, and we choose an indicator, something that will change color when we reach the equivalence point. That is called the end point, because it doesn't have to be exactly at the equivalence point, just close enough. And we're going to use phenolphthalein. Right? And one of the questions in your document, I think, is, what is the chemical name of phenolphthalein in the IUPAC system? It's that long, so you just look it up and copy it down. That's all you need to do. But you also need to find out what's the pH range for the color change. When phenolphthalein is in an acid solution, which will be here in the reaction vessel, it's clear. But when the pH exceeds a certain value into the basic range, then it turns pink. And that color change tells us when we've reached the end point. You'll see it when we do it here. I'll do it for you in just a second. All right. So we're shooting for the end point, but we need to prep things properly. We don't want any contamination in our buret. We want nothing in there but our sodium hydroxide solution. All right. So in order to do that, we need to rinse our buret with some of this. It's been rinsed out with water, right? but we need to displace all the water that's in there and be sure that there's nothing left except sodium hydroxide. All right, so we need to rinse it, and I need to glove up because sodium hydroxide is corrosive. Safety, safety first. So let's glove up right here and here. Oops, backwards. There we go. All right, so now, like I said, it's already been rinsed with water. So this position for the stopcock is open. Anything we put in there will flow straight through. So what we want to do is close it, which means perpendicular to the direction of flow. Now we want to put a little bit of sodium hydroxide in there and rinse. I think the method says transfer some into a beaker, which we can do. And that's too small. But it is clean. I know it's clean. So here's what we're going to do. We're going to transfer some sodium hydroxide solution into this. There's a little bit of water left in here. So I'm going to fill it up. And the first couple of rinses will have a little bit of water in it, but the last rinse will have none. And that will be the one that's definitive. It will finally clean things out. We want to be sure that we get it in the burette and not all over everything, so we use a funnel. And let's drop the burette down a little bit so that we can reach it easier. All right, so here we go. How much have we put in there? That's good enough. That's about 10 milliliters. All right, so we'll take this, sit it down there. Now, how do we rinse that? Well, you got a gloved hand, cover the end and rinse by rocking. Okay, one more time. There we go. Now my hand's got base on it, of course. And we put it back in the Buret holder. That's what this is called. It's a Buret Clamp, actually. And it's set up so that you can have two burets up here. Some titrations you do with an acid one way and a base the other direction. Those are for acids or bases that are slightly insoluble. So they become more soluble as you add their counterpart. So what you do is you titrate past the endpoint, and you note exactly how much that is, and then you take the opposite, acid or base, opposite to the one you just titrated, and you come backwards, and you come back to the endpoint from there. And that way you can say, all right, I know how much I put in here, I know how much I put in to come back. That's the equivalence point right there. But we're not going to do that. We only need to do one. So we got a Buret clamp, and now we're going to run it out the end and clean out the tip. Okay, notice that there is a bubble in there. We got to get the bubbles out. There we go. They're hiding up here in the stopcock. It's still running. You can see it running, I hope. So we just tap to be sure all those bubbles are driven out. You don't want any air bubbles in there. You want only base, top to bottom. I think we got them all. At least I hope we did. This is a nice stopcock. It's Teflon moving parts with the stationary parts also made out of Teflon. So when you have no difference between the materials, there's less. Uh-oh. See what I did? I let a bubble introduce. So we got to get that bubble out of there again. We need to do another rinse anyway. So let's add some more base. And here. We'll add a bunch this time. Okay. Now, one more time. And then I think what I'll do is I'll toss the extra in that beaker and use fresh for the last rinse. Okay. Okay. Yeah, oh yeah. Those bubbles are gone. That's good. So while that's happening, this is not very concentrated, so I'm going to that with lots of water. And now we're going to need 50 milliliters to fill that up. So I'm going to put maybe 60 or 70 milliliters. That base. Okay. We're still draining. So here's our citric acid. It's a solid. All right, I'm going to show you how to deal with that later. So put that over here because we need to measure out the precise amount 3 times. These are Erlenmeyer flasks. Let's see. Some of them, they've already got numbers on them. Here's a Roman numeral 1. Here's a... that'll be Roman numeral 2, and here's Roman numeral 3. And these will be Arabic numbers. Oh, here's a 2. Here's a 2. So these will be 1, 2, and 3, Arabic. So I use different numbering systems just so I can keep them separated. So this time, I'm going to stop it before I get a bubble trapped in there. It's coming right down to the bottom there. Now we're going to add a little bit more. I probably should have put more in here than that, but that's okay. And this is our final rinse. Doesn't take much. And now we're going to. So we've gotten rid of all the contaminants, all of the water that we used to clean, and our Buret should, once we refill it, should contain only the sodium hydroxide. Is that going to be enough? Yeah, that'll be enough to fill up our Buret. Let's see. I'm going to wait. Try to do too many things at once and you end up making mistakes. So let's watch this down till it gets right down to the bottom. So we don't want to introduce any bubbles in the end. There we go, there. Okay, now what I was going to do is I was going to pick up a dark object like this case from my calculator, and the reason for that is a dark background makes it easier to see the numbering. Right? So you can read your volume much easier. So that's what that's for. Okay, now we're going to fill up this Buret, and I'm going to fill it up past the mark and bring it down to the mark. Okay, so we need a funnel, and we're going to add our base. So you have to be able to walk and chew gum at the same time to do this type of chemistry. Here we go. We're getting there. We're getting there. Let's go up past the mark. There we go. So let's set this aside where it won't tip over. Right there. And pull this out. Right there. And now, next thing, I'm just thinking ahead, so pardon the dead air. We're going to be using these chem wipes. If you've never used a chem wipe, it's a specially made laboratory tissue that is lint-free and anti-static. Right? They're very, very clean. They don't introduce any particles of their own. They just absorb liquids. So we're going to use those, and I'll show you how in just a second. All right. So I want to move this down a little so I can see it better and set this on the 0 mark right there. Notice that you need to be eye level, and the way that you can tell that you're eye level is for every milliliter mark, the scoring goes all the way around. So if you're below or above, you're going to see 2 lines. Right? You'll see 2 lines. If you only see 1 line, that means your eyes are level. And of course, you always want to read aqueous solutions at the bottom of the meniscus. Okay, so now I'm going to bring this down slowly until we're on the 0 mark. I'd like to start on 0. We're going to do 3 titrations. So there it's coming down, and I'm going to slow it down a little bit like that. There. Now what else do we do? Well, we want to come up where we can reach it, and you just remove any clinging drop to the end of your burette tip. That's it. Now you're ready to go. Okay, so what we want to do is we want to have exact volumes of the known acid in each of our Erlenmeyer flasks. Right? It doesn't matter that there's a little water in there because I rinse them out just to be safe, so I don't want any contamination. Why? It doesn't matter the volume because you're looking at moles of base against moles of acid. The concentration doesn't matter. So I need another beaker, a clean beaker. Actually, I need one that's dry. You know what? I know this one's clean. It's just not dry yet. So that's what I'm going to do. I'm going to dry it. I could use a different beaker that's dry, but then there's always the question of who used this thing last and did they clean it? And the last thing I want to do is an experiment with dirty glassware. There we go. Let's see. No, I already used that for base. I'm use a clean one. Be sure all the moisture is out. Now, why I just said that moisture doesn't matter. Moisture matters when you're trying to establish a known volume. So I need this to be undiluted. Once you get it in the reaction vessel, you can dilute till the cows come home. But this is used for dispensing. Right? So what I pour in here is not going back in the bottle. You never put reagents back in a bottle like that, or you could contaminate your stock. So there's our acetic acid. And now, here's a clean, dry, 10 milliliter volumetric pipette. And we're going to do 3 times 10 milliliters in each one of those. Here's a pipette bulb. These things are nice. When I was first studying chemistry, we didn't use one of those. We mouth pipetted. We just sucked it up. Okay? That sounds stupid, I know. But that's what we did. Now we have these devices, so if you pull it up too far, it goes into the bulb and not in your mouth. Okay, so it has 3 valves on it. The top valve is A for aspirate. So you squeeze that and then press on the bulb, and that charges it. Once you release that, then it's ready to suck. And that's what the S is underneath it. This is for sucking up your reagent. Okay? Then once you get it up here, you release pressure or suction on the top, and it allows it to drop until you reach the calibration line. Okay? So you need all 3 of those. We charge the bulb first. Now we're going to use the suck, and we're going to bring it up. Here we go. Up, fast, fast, fast. Now slow. Now it's going to go fast. So you have to be careful. You don't want to suck it up into the bulb, unless it's by accident, of course. Okay. Now we're up there. Now, at this point, I grab the E for expel. That's what E stands for. And then I press on it just slightly, and it will drop. There, that's a controlled drop. And I'm looking at this against a light background so I can see. There we go. Right on the meniscus. And you also want to clean off the tip here. Now, when you deliver this into your flask, all you have to do is hold the E down and let gravity do its thing. These pipettes are calibrated to deliver. So that means you let it go down to the end, and then you touch the tip, and that's it. Anything left in there is accounted for in the calibration process. So that's 1. We need to do that again. All right? So we'll go in here, and we'll suck up 10 more milliliters. And let's see. Here we go. Actually, yeah, that's right. I'm doing it right. I'm just checking myself. 10 milliliters. And we remove any clinging to the outside. And Erlenmeyer flask number 2. Expel. They make these volumetric pipettes in monster sizes. I used to have one that was 100 milliliters. It was big. Sometimes I had to squeeze that bulb 2 or 3 times to get it to fill. Okay, here we go. The last one, the 3rd one of our sodium hydroxide calibration amounts. Okay, so now we're going to come down, 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 down. Eye level on the mark. And then we want to pick up any extra on the outside and deliver. Expel. All right. Now, I'm going to check my camera battery. So there'll be some movement here. Very good. Still got half a charge left. So we'll go ahead and do our calibrations. Now this is acetic acid. We're not going to put it back in the bottle, but I do want to keep it close to its mothership. This one we're done with for acetic acid. So what we'll do is rinse it out. Right? Distill water. Clean the outside down where we might have touched something, and then rinse 1, rinse 2, and rinse 3. Okay. Now let's see. Let's at least clean off the outside. And let me hold it firmly. Maybe shake a little bit. Okay. Now, what do I want to do with this? I'm going to lay it down over here. There we go. Well, I had 2 of them, just in case there was something wrong with the first one. But I don't need this one, so I'm going to lay it down here. And we'll put it in its protected cases later. All right. So there's our waste beaker, of course. And we're down to, right? So we need to be sure that there's nothing clinging to the tip. Right? Now, we're going to titrate. Now, the method says that you and your partner do this together, and one of you holds it under here and keeps mixing it. But I'm all by myself. So I've got a stirring hot plate, which means that underneath that plate is a big magnet. And it magnetically couples with this Teflon-coated stir bar. And the stir bar sits in your flask. This was a pretty big one, but it's the only one I could find. A smaller one would be better, but no use complaining. We're going to put this in here. Hold on just a second. I think it calls for yes, it calls for diluting the sample with 10 milliliters of water. Right? And the 10 milliliters of water does not have to be exact. So we're going to use a graduated cylinder, and I think that's because you need enough volume. Well, I definitely need enough volume for my magnetic stir bar, but you need enough volume for the procedure, just so that the you don't go past the end point. It's easier to go past the end point with small volumes than it is with large volumes. So let's fill this up to 10. And we'll be reasonably accurate with a graduated cylinder. There we go. So here's number 1. One other thing, if you, while you're adding anything to this Erlenmeyer flask that you want to enter into the reaction, it's okay if it happens to hit the side of the walls of the, just to rinse it down like that, right? Because I said the volume doesn't matter now. We've already established how much acid is in there. Now we put our clean stir bar in there, set it on here, and start it spinning. You won't have to spin very fast. Okay. I want to be sure. Yeah. I want to be sure that the tip is over the mouth. We can go a little bit faster. There we go. Now, that should be plenty fast to keep things mixed. Now, the one thing I haven't put in there yet is the phenolphthalein. That will indicate when we have reached the end point. So a couple of drops is all that's required. One thing you may not realize is that phenolphthalein is a weak acid itself. So it's at the same time as your titration reaction is going, the phenolphthalein reaction is also going along with it. Only it doesn't take as much. Just a little bit of this will give you the color indication so it doesn't interfere with your main reaction. Okay, notice that it's clear because that's an acidic solution. Right? So now what we're going to do is, actually we put 10 milliliters each of acetic acid in there, and that's what we're going to mark here. 10 milliliters. And why did I write milliliters again when it's already in the heading? I'll show you. Because if you multiply milliliters times molarity, you don't get moles. You get millimoles. Okay? And that's okay. If you have molarity of the acid and molarity of the base, and the volumes cancel one another out. So it doesn't matter that it's milliliters. If you're more comfortable, you can convert that to liters, and liters times molarity is actually moles. Okay? So now we're going to determine the volume of base that's required to neutralize 10 milliliters of our acid. This is our unknown for now. Once we know that, then we can calculate the unknown molarity of the base. Okay, so let's get down to it. And you'll notice that as we proceed, let's bring that a little bit closer, like that. There we go. Now I feel more comfortable. Okay, here we go. In the beginning, you can go pretty fast. And I don't know if you can see it, but with each drop, you get a pink color developed until the mixing is complete. And then the pink goes away. As we get closer to the end point, the pink will be more persistent before it disappears. And when we actually reach the end point, one drop will go from clear to pink and stay pink. That's the magic in this type of titration, being able to find that endpoint. Now, if we had sodium hydroxide was in the neighborhood of 0.873 molar, and our acid is 0.873 molar, then if we put 10 milliliters of this in the reaction vessel, we should expect in the neighborhood of 10 milliliters of this. But this is less concentrated. So it's going to be past 10 milliliters, which means I can go a lot faster if I wanted to. I just have to watch the volume, all right, so I don't overshoot. Okay, we're coming up on 9 milliliters. Notice that the pink is persisting a little bit longer. Okay, let's give it a chance to react. There we go. Looks good. And let's do dropwise. There's a drop forming now. That's good. The whole idea is control. So we're hitting, right now we're at 10. Coming up on 10 and a half. Okay, I'm going to stop that. And we're going to go dropwise now. I do not want to overshoot. Nerve-wracking, isn't it? Let's do one more and then stop and observe. Okay. All right. Let's do another one. See, now once we get one titration done, then the other replicates will be easier to get to, because we'll know closer to where the endpoint should be, and we can go run down just above it, and then slow down for the final push to the endpoint. Okay, we're down below 11 now. We ought to be getting really, really close. But this first one is the nerve-wracking one. If you have to do several hundred of these in a day, you get pretty good at it. And nowadays they have machines that'll do it for you. They take all the fun out of it. The pink is persisting longer and longer. Oh yeah, we're very close. Another drop. Another drop. I thought I saw some hit the edge over there, so let me... No, we're good. Okay, another drop. Oh yeah. We're getting there. Oh man, were we close. Oh, maybe one more. Maybe two at the most. Okay, let's deliver one drop. Is that it? Yep, we hit it right on the money. Okay, what's the volume? Okay, where's my dark? I've got, reading from the top down, 11 point, let's see, where's the mark? There's 12, there's 5, 11, 5, 6, 7, 11.7 milliliters. 11.7 milliliters. Okay? Now, the next one should go a lot faster, because we know how close is close. Let's rinse off the tip. Oop, let's stop the turning. Rinse off the tip and dry the tip. There we go. Now we're ready for the next one, and let's check our volume. Yeah, 11.7. So 11.7 is our starting point for the next one. We started at 0, so our delivered volume was actually 11.7. All right, so there's one. So let's put 10 milliliters in the next one, and we'll knock this one out pretty fast. Okay, 2 drops of phenolphthalein. 1 and 2. And we need our stir bar. How do you get the stir bar out of there? Well, you could dump it and catch it with your hand, but I've got this magnet, plastic coated magnet. I just reach in and grab it. And then while it's on the magnet, I rinse it off. Okay. There we go. Now this one goes in the second one. Here. There we go. Now let's start this thing spinning. Okay. Now, what is 11.7 plus 11.7? Well, it's 23.4. So now we want to go down to in the neighborhood of 23 before we start getting careful. $16, $17, $18, $19, $20, $21, $22. Let's check ourselves. Yep, it disappeared. And $23. Yep, we're good. Okay, now we can slow her down and not watch the volume anymore, but watch the reaction. Oh, that did it. It's 23.4, right on the money. 23.4. Okay. Start a new titration. 23.4. So 23.4 is the reading and the volume, as a consequence, is 11.7, exactly the same as the first one, right? So if we do the same thing for this one, where will it end up? 11.7 would be 35.1. So we're expecting 35.1 for the next reading. All right, so we need... Okay. Just as I feared, the battery went out, but I think it picked up the first two titrations of our calibration. So now I need to pull this out here, clean it off, and I need to check my battery more often because I don't want to miss a thing for this. Okay, I did put phenolphthalein in that one, so it's ready to titrate. And let's check 23.4. Good. So we're ready for the third titration. Starting point at 23.4. Wherever it ends should be, what did I say? 35.1. Okay. So let's go down Am I seeing any pink? Yes. There's the pink. Passing 29. Passing 30. .32. We're headed to 35.1, remember? Down, let's stop it at 34. Okay, we are getting pink, so that verifies I put the phenolphthalein in there. Alright. Let's drop it down there. Okay, now we're going to go slower. Start it, drip, drip. There you go. I don't want to go past. It's almost to 35. So let's do drop at a time. Let's see. I need to tilt my head a little more so you can see this. Here we go. Let's try one more. Let's rinse that one off of there. Oh my. That is so close. Let's do a half a drop. Oh yeah. We nailed that one. Okay. Now we read 30. Where's my 5? Actually, it's a little past 35. It's not quite. .05. I'm estimating 35.05. So that means that we're not quite 11.7. We're 11.6. Well, let's see. I'm getting over into the other column. 11.65. All right, so those are our 3 values of base volume. Okay? So let's do a cleanup. Not a complete cleanup. Let's do a short cleanup. Actually, it probably would be better, considering my battery wants to run low, to set the cleanup aside. Like that. Set these out of the way. Okay, and get ready for the citric acid. Okay, we use the same technique for the citric acid, except now what I want to do is refill the burette, right? Because we don't have enough capacity now to do 3 titrations at once, so we're just going to fill all the way back up to 0 with the base. We'll save our calculations for later for the same reason. I don't want my battery to run out again. I just got lucky on the last one. I don't think I missed much. There's base. And let's fill her up. Okay, there's our one. Let's see, I don't have 2 on this one. 2. 1, 2, and 3. All right. So that was the standardizing part. This is the titration of the citric acid. So for the citric acid, we have to weigh it out, get a mass for the sample, transfer it into the Erlenmeyer flask, and then dissolve it in water, because the reaction won't take place in a solid, not efficiently. It'll only take place wherever the wet of the titrant is touching it. So we want to put it in solution. We're going to go for about 0.7 grams, and we're going to measure that as accurately as possible. And then dissolve it in 25 milliliters of water. Okay? So this one's not big enough. This is only a 10 milliliter volumetric. So I'm going to use this one so we can get 25 milliliters. And let's just get this one ready. It's had nothing but water in it today. And again, the volume, exact volume, doesn't matter. What matters is the mass of the citric acid. Right. So that's ready and waiting, and we need to, we're not going to weigh directly into the flask, of course, so we're going to set this to 0. The container is now zeroed out, well, as soon as it settles down. And we're shooting for 0.7 grams. Now, the thing about this one is the mass that we're putting in here in each one of our samples is going to be slightly different. So we won't know exactly where the endpoint is each time. So we'll have to stop advancing and slow it way down a lot sooner. Okay, 0.7 grams. There's our citric acid. And this is the same stuff that makes oranges and lemons sour. One of the things that makes them sour. Very close. The closer we can get to each measurement being the same, the easier it'll be to titrate. So let's close the lid, cut out the drafts. .709. 0.709 is the mass of our citric acid. 0.709 grams. Okay? Now, how do we make sure that that's transferred completely? All you have to do is turn this weigh boat into a funnel, like that. Get as much solid in there as possible, and the rest of it is rinsed down with your wash bottle, right? Because the volume doesn't matter. And this quantitatively transfers everything that we measured into the Erlenmeyer. Okay, now we're going to add the extra water. that, and let that be dissolving. And while that's dissolving, we're going to weigh out another one, the second one. You use a fresh weigh boat each time. Okay. And what's it doing? Drifting. There we go. 0.7 grams. Very close. Close the lid, cut out the drafts. Zero 0.702. 0.702. 0.702 grams. Okay. And we'll do a quantitative transfer of this one into Erlenmeyer number 2. Okay, now we need 25 milliliters approximately. And there we go. Here we go. That dissolving, that dissolving. One more. Okay, are we on 0? Trying to drift on us. There we go. 0.7 target. Creeping up on it. Very, very, very close. Can I get one grain? Let's try that one. .70. 6.706. Okay. We got pretty close. We know that whatever value we get for this one, volume added, these two are going to be less than that by just a little bit. Okay, we got our mass. Now let's quantitatively transfer this last one into number 3. All right. Now we need 25 milliliters of distilled water. Here we go. Now, by the time we need those two, they'll be dissolved, and I think this one is probably, oh yeah, that's in solution. So that we don't forget, let's put phenolphthalein in all 3 of them, and we don't have to think about it anymore. 1, 2, 1, 2, 1, 2. Now we're ready to roll. Okay, I'm going to rinse this out because it's had base in it, and I'm not going to need it anymore. So let's clean it out. In fact, we haven't yet set the 0 point on this volume. So I need to bring it down. And they get level. I can see it pretty well because the blackboard is behind me. So let's bring that down to 0. There we go. Now, what do? We dry the tip. Just take off any drops that are waiting. Transfer. And let's see. Let's raise up a little bit and then come down a little bit. There we go. Now start her spinning. Mixy mixy. That's good. Now let's watch how the color develops. Oh, I got a fresh one here. Oh, before we do that, let me check my battery again. Okay. So far, so good. I'm going to check it after each titration. That's how paranoid I am. So if we watch the color, and it's very well mixed, we can see when we're getting close. All right? I barely see pink, and it just goes away almost instantly. I'm going to stop that for a second. We've added a little over 9 mils. We'll do dropwise now. Down below 11. More persistent pink. I don't know how if you can see this very well. I really want you to see what's going on here. Here we go, dropwise. Let's see, we're down 13 milliliters. And still going. Getting closer. That's 13 and a half. We're very close. 14. Could happen any time now. Oh, yeah. All right. Oh yeah. Next one might be it. Let's try one more. Oh my goodness. Is that it? Yep, I think that's it. Okay, let's read the volume. We're at 14.9. 14.9 milliliters of base delivered. Okay, Now this one's going to take less. So if it were the same amount, it would be 29.8. So we're going to go maybe to 28 and stop, and then go slow. Here we go. Okay, come up there like that. Like there like that. Snag that stir bar. 1 down, 2 to go. Okay. All right. So let's drop it down here like that. There we go. And start it spinning. What did I say? About 28? $27, $28. Okay. All right. So now we're going to add it dropwise. It's touching the edge of my flask. It's messing up my drops. So let's get everything back down into the reaction and see if I can there we go. Steady drip, drip. That's 29. See some on the walls. Gotta rinse it all down. There we go. I want to hold it because I think that magnet is kicking it around. So let's hold it steady. Oh, we're very close. Drop, drop. One more. One more. Okay. Yeah, we're on the doorstep. Very close. Drop. Next one might do it. Whoa. Almost. Let's do one more. That was the one. Now let's read our volume. Let's see, it's not to 30. 29. 0.5678. 29.8. 29.8. Okay. Let's see. See it. 29.8. Which means 9. And take away 1 8, 4 from that, 4. 14.9. So that, see, this is grams, so that's milligrams. So a difference of 7 milligrams doesn't make that much difference in the milliliters of base delivered. So this one should be in that same neighborhood. So 14.9 plus this would be 34.7. 34.7 is our target for the next one. All right. So let's see if I can do this, yeah, like that. Just make sure there's nothing hanging on. And we'll want to extract the stir bar and rinse it off. All right. Get in that crack there. There we go. Put that one in here. And what did I say? 34.7. Let me check my camera. Okay, I'll tell you what I'm going to do. Before we start this titration, I'm going to stop the video and change batteries. Okay. Now, we're ready to do our third titration. I shouldn't have done that. Hold on a second. Put my glasses off, and now I can't get them back on. There we go. So now, put that under there. Start the okay, what did I say? We should be in the neighborhood of 44.7. Here we go. I'm gonna sit down, gang. Here, how about that? Okay, we're getting very close. So now I'm going to have to stand back up so I can see the drops. Let me rinse down everything. Yeah, there we go. All right, now let's start making small drops in succession. Very slow drops. Oh, we're so close. I'll stop after this one. Yeah, maybe one more. Oh, missed my guess. Comes another one. Yeah, that was it. Now let's read. And I see, where's my marks? 44, and there's 45. There's 1, 2, 3, 4, 5, 6. 44.6. 44.6 reading. Let's see. 44.6 means 29.8 from this one that's 8. And then 9 from 13 is 4. 14.8. Okay. So my guess is that we have some experimental error in here. One of these. But they're very close together, so we're going to keep them all. Okay. Now, in order to determine the moles of base, we need the molarity of the base. Right? So we have to calculate that before we can proceed with the rest of this one. All right. So let me stop this spinneroo like that, and we'll put the waste beaker underneath it. We'll pull this stir bar out, rinse her down. Okay. There. Okay. So those are used, and we'll leave them there. That's it. We're done with the experiment. Now what we have to do is the calculations. So, let's do this part, and then I'll check my battery again. All right, so I need a piece of chalk. Okay, so this says moles of acid. We're actually going to calculate millimoles. So millimoles is just molarity times milliliters. So 11.7 times 10 is 117. 3 degrees of three significant figures. 117 millimoles. Okay? This one is 117 millimoles. And like I say always, never throw a decimal away until the very end. So this one is 116.5 millimoles. All right? So, for sodium hydroxide and acetic acid, the moles are equal because one of these for each one of those. I showed you the reaction. That's it. So this is 117 millimoles. This is 117 millimoles. And this is 116.5 millimoles. Okay? So if this is millimoles and we need molarity, that means this value is equal to molarity times volume of the base. Is that right? Oh, my goodness. I am so stupid. Can you believe I made such a rank amateur mistake? What's the moles of acid? 10 times 0.873. This is the molarity of the acid. This is the volume. 10 times that is 8.73 millimoles. And it's the same for each one. Right? I'm pretty sure that's right. Okay. So how many millimoles of base are there? The same amount, because they're equal. And if you divide millimoles by milliliters, you get molarity. Moles per liter, millimoles per milliliter. Right? So this is millimoles, this is milliliters. Divide millimoles by milliliters, and you get molarity. So I need a calculator for this one. 8.73, 11.7. 0.746. 0.746 molarity. 8.73 divided by 11.7, same thing. 0.746 molar. And then 8.73 divided by 11.65 is 749. 0.749 molar. Now, what's the average? Those are pretty close together. We're just going to take those as the average. 0.746, add another one, and then 0.749 divide by 3. 747. 0.747 molar. Right? Nominally, it was 0.75. So it hadn't changed that much, really. We must have treated it very well and kept the air away from it. That's the key. Okay. So now that we know the molarity of the base, then we're actually going to have to calculate moles here instead of millimoles. So that means, what are the number of liters here? So this would be 3 to the left, 0.0149 liters. Same thing. 0.0149 liters and 0.0148 liters. Okay, that's the number of liters of base that was used. So we know that that's the liters, and this is the molarity, so volume times molarity equals moles. So 0.747 times each one of these. .0149 is 1.11 times 10 to the minus 2. 1.11 times 10 to the minus 2 moles. Right? Same for this one, because it's the same volume. 1.11 times 10 to the minus 2 moles. And 0.0148. 0.0148 times 1 rounded off. it's also 1.11 times 10 to the minus 2. So how many moles of acid, of citric acid, are there? Remember we said 1/3 of this. So we have 1.11 to the minus 2, And since they're all the same, we just take a third of it. 3.70 times 10 to the minus 3 moles. It's the same for each one. Okay? So if it's the same number of moles, the only thing that's going to make a different molar mass is the mass, because it's mass divided by moles, and the mass is different, but the moles are all the same. All right, hold on just a second. I'm going to check my battery because I'm paranoid. Okay. Looks like we got half a battery left, but don't let that fool you. This thing can crash at any minute. So let's get this done in a hurry. So, mass divided by moles is molar mass. So, let me put this one in, let's just have a bunch of them. 0.709, enter. Divided by that number is, well, that can't be right. Try that again. 0.709, enter. We'll just put them in fresh because I hit the wrong button for some reason. .7, and that's the moles divided into the mass. That's more like it. 191.62 grams per mole. Okay? Now 0.702 divide by the same number of moles. 1.8973. 189.73. And then 0.706 divided by the same number of moles is 190.81. 190.81. I think those are close enough we can do an average. So let's see. 191.62 189.73. Oops. Try that again. 0.73 plus, and then 190.81 plus, divide by 3, 190.72. 190.72 grams per mole. All right. Now, when you write your report, of course, you better show me all this work. Don't just regurgitate it. Okay, how do we tell the percent error? After I check my battery again. Okay, we're still good. I need to get bigger batteries. How do we tell percent error? Percent error is equal to the accepted value. Is that right? Hold on a second. Accepted minus experimental. No, it's the other way around. Experimental value minus accepted divided by accepted times 100. Now, why do I do it that way? Well, if you do it this way, if the experimental value is smaller than the accepted value, then you come out with a negative error. Right? And that negative value says that your experimental is less than your accepted value. And if the experimental is larger than the accepted, then it gives you a positive value for your error. Now, of course, some instructors don't care about that. They just say, all right, just give me this. How far off was it? Absolute value. Then it doesn't matter which order you do it in. But we're going to do it so that we get a sign. in front of our error. Okay? So what would that be? Experimental is what? 190.72 grams per mole minus 192.13 divided by accepted. 192.13 times 100. Okay? So let's see. I've still got that one in my calculator. Let's say 192.13 subtracted from that, and 192.13 divided 100 times. And that is 0.734. 0.734%. Less than 1% error. That is very good. Okay? So, let's look at the document and see if there are any questions there that might need some. Oh, I'm about to run out of battery. Look at that thing. It just all of a sudden it crashes. So I'll be back in just a second. Okay, I'm back. This is frustrating. I want a battery that lasts 3 hours. Okay. So the questions that were asked, laboratory questions, compare your experimental molecular weight with the true molecular weight. Are they the same? Why or why not? Okay, we've done that with our experimental error. Now, if it's not the same, why is it not the same? All right, can you think of any reason why it would not be the same? Well, there are numerous points in here that all speak to experimental error, right? Because we are judging the endpoint by a change in color. It's a judgment call. We are reading our Buret. That could be, we could be looking at an angle. That's called parallax error, where you look at, instead of seeing one line on our tube, we see two lines. That means we're either too high or too low. That's called parallax when you're off center. What other kind of error could there be? Well, I guess we could go all the way back to acetic acid. Maybe that's not the right value for acetic acid. I mean, I have to trust the manufacturer. How about measuring out 10 milliliters? Right? That had a 0.04 milliliter error, which is not really much. But I'm just grasping at straws. Could we have made a calculation error? Right? Because these are not exactly the same values. These are different weights. Right? What about purity? Is our citric acid pure? Right? We think we have 0.709 grams of citric acid, but maybe we don't. Maybe we only have 0.700 because of impurities. So if we're saying it's larger than we think it is, then this value is going to be larger than expected. Now that would make the value even greater percent error, right? And this is a negative, by the way, because this value is less than that value. Okay, think about it. Think of other possible errors. Why was a volumetric pipette used to transfer acetic acid and not a graduated cylinder? Right? I hammered that one hard enough. You ought to be able to figure that one out. Let's say you see a classmate use 29, 30, and 31 milliliters of distilled water to make up the 3 acetic acid samples. How will this affect the experimental molecular weight calculation? What have I been saying all along? after you've measured out your acetic acid with this accuracy, any further dilution you make means nothing, because it only matters how many moles you have. How would the experimental molecular weight be affected if the acetic acid were impure? Well, if the acetic acid were impure, we think we have 0.8, but maybe we only have 0.873. We only have 0.8. So what would that do to our calculations? We've got 10 milliliters. Let's say that's right. And we're saying 10 milliliters of acid. Here, it should be 8 instead of 8.73. This should be 8 instead of 8.73. So this would be moles divided by milliliters. So if this is actually less than that value, then this is overestimating the molarity of our acid, or of our base. It's overestimating. So we don't have as much base as we think we do. And it takes more base to actually neutralize than we think it does. Right? So this overestimates the amount of base you need. It should be less than that. Less base is actually required because we've overestimated it. So that would mean that the number of moles here, this is liters of base, so this would be liters times molarity, and that would give you a value that is less here, should be less there, and less here, would give you fewer moles of base required. Right? So this would be less, this would be less, and if that's less, what does that do to the calculation? The less part is right here. So in the denominator, if the value is smaller, then the true calculation that you would make would be larger. These values would be larger. Right? This value would be larger, and it would be closer to this value. So that seems like a plausible explanation for impurities if the acetic acid were impure. Right? So maybe the acetic acid was impure because it gave us a lower value than we should have gotten. There are other ways to standardize your base using a different acid. In fact, the best way to do it is with a solid that can be weighed out. It can be heated and dried and then cooled in a desiccator and weighed out very accurately before you use it to standardize a base or an acid. Okay, so let's go on to number 5. How would the experimental molecular weight be affected if some titrant were dropped on the side of the flask during the titration and not rinsed into the solution? I don't want to steer you guys wrong. So let's go back to that other one. If impure acetic acid, then what we've done is depressed. We've depressed the value of molecular weight that we calculate, and that's what actually happened here, we think. So what about another possibility? If you drop some of the some titrant, the base, on the side of the flask during the titration and not rinsed it in the solution, well, you think your volume is higher than it really is. So that says you have more moles than you think you do, and it needs to be decreased. And there again, with a decreased number in the denominator, your value should be higher. It's actually depressed. So for the different reasons, the answers to 4 and 5 are the same. Okay, those are the only questions. And that is the completion of molar mass of an acid by titration.